To be able to predict the contour diagram for C2Cl2, we will have to go through multiple steps, starting with Lewis structure, moving on to the VSEPR diagram, and then going through the hybridization for the central atoms, leading to the contour diagram. To start us off, we would have to take a look at the Lewis structure of this molecule right here, which would mean that we would have to figure out the valence electrons for our molecule. Starting off with carbon, we know from the periodic table that carbon has 4 electrons, valence electrons, and we can see here that we have 2 of those, which is going to mean that we're going to have a total of 8 electrons for carbon. And for chlorine, we know that it has 7 electrons, and we have 2 of those as well, which means that we have 14 electrons, giving us a total of 22 electrons for this molecule. So to draw the Lewis structure, we would have to start with a carbon in the middle. That's because that's our central atom for this one. And it seems like we do actually have more than one central atom, and each one of those carbons is going to be attached to a chlorine. And from here we can see that we are going to have 22 electrons minusing 2, 4, 6 electrons, giving us a total of 16 electrons. And then we're going to go ahead and place some electrons on the outer atoms of this molecule. Those are going to be our lone pairs. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18. So that means that we have 22 electrons minus the 18 electrons, meaning that now we have a remainder of 4 electrons. We're going to go ahead and place those last 4 electrons as a triple bond between the two C's. Now that we've made our Lewis structure, now we get to move on to the VSEPR diagram. Now VSEPR stands for valence shell electron pair repulsion theory. Now this was a theory that helped us determine the shape of our molecule, since looking at our Lewis structure not always gives us the accurate shape for a molecule. In this case, it does, since it looks the same way as we can tell right there, but in most cases, it doesn't actually work that way. Okay, so to determine the shape that our molecule is going to have as a VSEPR diagram, we need to look at our central atom, which in this case could either be this carbon or this carbon right here. Wouldn't really matter. They both have the same types of bonds. But either way, we can see that this one has a single bond right here and a triple bond right here. But in a total, it actually has only 2 bonding electron pairs, since this is a bond and this is a bond, meaning that this is going to be a linear shaped molecule, which also means that our VSEPR is going to end up being the exact same as our Lewis structure. The only difference in this case would be that we would have to include our angle, which, as we can see, it's linear, meaning that it's 180 degrees, and we would have to include the shape, and as we said, that is linear. Now that we know that our molecule is going to go ahead and look like this as a linear, having a linear geometry, now we get to move on to the box diagram. Now for the box diagram, we're going to have to look at our central atoms and how they're bonding. Now, our central atoms for this molecule is the C right there and the other carbon right there. I'm going to go ahead and make 2 different hybridizations, but they're going to be the same since both carbons are bonded the same way. Now, we know that carbon has an electron configuration of 1s, 2s, and a 2p that are filled like this. Now, in this case, we're not really going to be worrying about the 1s anymore, but all of our attention is going to be directed to the 2s and the 2p, since those are the levels that are going to be bonded to other atoms. At this point, we're going to go ahead and remove this sort of configuration, because we're going to go ahead and put it in a different way. So we're going to put our 2s right here and our 2p right there. Again, we're ignoring the 1s. Now, at this point, we're going to go ahead and add some energy. Now, the reason that we add energy is because the fact that at this point, all we can see is that our carbon only has 2 electrons that are ready for pairing. But if we take a look at our molecule, we have 4 bonds right there. Now, how do we get 2 to become 4? We're going to go ahead and promote one of these electrons to a higher level, opening up 2 spots for electrons to move into. Now, at this point, when we go ahead and do that, we end up with carbon in an excited state. Now, as carbon being in an excited state, it's going to go ahead and look like this. Now, as we can see, we have 4 different spots that are open. And we can also see that carbon is in fact ready to be hybridized. Now, when we hybridize it, we pretty much put it in a bonding state. This is the part where we get it to its final state before it's ready to be bonded. Before we hybridize, I personally go back and look at my molecule and see where I have single bonds, double bonds, or triple bonds. Now, from what we know about different kinds of bonds, we know that single bonds are in fact sigma bonds. And we also know that double or triple bonds have a single bond, that's a sigma, and it also has 2 other bonds, those 2 right there, that are in fact a pi bond. Now, we also know that only sigma bonds are involved in hybridization, and pi bonds are performed with, in this case, our 2p level, which means that we're going to have to leave 2 of those as 2p, and we're going to have to hybridize only these 2 right there. Now, when we hybridize these 2, we're going to put them at a level that is between 2p and 2s, meaning that it's going to end up being somewhere in the middle right here, and that it's going to be 2 lone electrons that are ready to be bonded. And as we said, we have 2 right here that are ready to be bonded as pi bonds. Now, we need to not forget that right here, this is an sp, or level, and that one exists between the 2p and the 2s when one of the 2p and the 2s are hybridized. At this point, we have hybridized one of the carbons. I'm going to go ahead and hybridize the other one so we can go ahead and move on to the next part. Now, as we can see, I have both hybridizations for the carbon atoms. Now, I went ahead and wrote them down on the side just to make it a little cleaner when it comes to the bonding. Now, we know that we have a carbon, another, and we have 2 chlorines. Now, to bond with the chlorine, we're going to consider only the last level of chlorine, which is 3p. We're going to fill that in like normal, and we have another chlorine that is filled in just like that. Now you can see how one of those is going to be bonded to the carbon. But at this point, we need to go back and take a look at our molecule and remember that the bonds between the carbon and chlorine are in fact sigma bonds, and that goes for both sides. Now that means, as we know, that sigma bonds only occur and happen with the sp level. That also tells us that this electron right here is going to bond with either this one or that one, doesn't really matter. Now I'm going to go ahead and bond that right now for both chlorines. Now that that's bonded, now we can see that we still have those lone electrons right there. So let's take another look at our molecule. We can see that our molecule is going to have another sigma bond and 2 pi bonds. Let's go ahead and do those. So as we said, sigma bonds, meaning that these bonds are going to be between the sp, and that is going to happen right there. And this is also going to be a sigma, and these were also sigma bonds. That leaves us with the 2p bonds, or electrons, that are right there, and those two are going to be bonded to each other. Those four, sorry. We can see how that one can bond with this, and we can also see how this one can bond with that. Now that's going to be a pi bond, and this one is also going to be a pi bond. And that is the way that our molecule is bonded to each other, and that's the way that we can establish our contour diagram. Now that we've checked off Lewis structure, VSEPR diagram, and the box diagram off our list, now we get to our final step, which is the most important, which is our contour diagram. Now, I have some pictures here from the app, and you can see the 2 bonds right there. There's one, and the other one is in the back, and another side is right here. There's one, and there's the other one right there. But again, we need to know how to draw on our own. So I'm going to go ahead and draw a line right in the middle. Now, you would want this line to be as straight as possible. And as we remember, we have our C's right there in the middle. And let me zoom in a little bit. Between those C's, we have one bond right here, and another one that is right. Let me fix that line a little bit. Our other bond is right here. Now we need not to forget that we have electrons in the middle right there. There's one right here, and there's another right here. And we might as well label it while we're at it. So those were the sp bond that happened between those carbons. Now let's go to this carbon and bond it to a chlorine. So we have our sp along with the electrons in the middle, and it labeled. And at this point, we can go ahead and bond that to a chlorine. Now chlorine came from a p orbital, which means that it's going to have this shape right here. Now we're going to go ahead and label that chlorine, and this one was 3p. Now let's go ahead and do the same thing on the other side with the other chlorine. So we have this right here, our sp level, and we have bonded to it our carbon that comes from a p level that has this shape right here, and it was a 3p, and it was a chlorine. And we need not to forget to label our bonds, what kind of bonds we have. So this is a sigma bond. This one in the middle as well was a sigma bond, and that right here was also a sigma bond. Now this is the part where we get to our pi bonds. Now to make our pi bonds, we have to focus on each chlorine. And I'm going to go ahead and make it in blue. It's going to go like this. And we don't want to forget them at the bottom. And I'll go ahead and make this one right here as well. And each one right there has an electron, meaning that this right here, this one right there, is going to have an electron right up there, and this one right here, I'm going to go ahead and put its electron right there. I'm going to do the same one for the other side. Now that we've done that, we can just go ahead and overlap them, since that is the way that they bond. And we're also going to go ahead and label them. Now, after all this, we never want to forget that we still have to include the angle, which is 180 degrees, and also we need to include the shape, which is linear. This way, we would have our final and completed contour diagram for C2Cl2.